The purpose of this video is to compare the two means with independent samples. We assume that the statistics are already computed for us. People spend around $1 billion annually for the purchase of magnets used to treat a wide variety of pains. Researchers conducted a study to determine whether magnets are effective in treating back pain. Pain was measured using the visual analog scale, and the results given below are among the results obtained in the study. Assume normality. Use a 0.05 significance level to test the claim that those treated with magnets have a greater mean reduction in pain than those given a sham treatment similar to a placebo. Does it appear that magnets are effective in treating back pain? Is it valid to argue that magnets might appear to be effective if the sample size are larger? We are given the statistic for the two samples from the two subpopulations. The first subpopulation is the one with the magnet treatment, and the second subpopulation is the one that were given the sham treatment. From each of the subpopulations, we'll get random sample. For the first subpopulation, we computed that the sample size is 20. Not that we computed, but they were given to us. The sample mean reduction in pain, y sub 1 bar, is 0.49, and the standard deviation s sub 1 is 0.96. Even though it was not denoted as n sub 1, y sub 1, s sub 1, but we include the subscript sub 1 to distinct sample 1 to sample 2. Similarly, with the second subpopulation, they obtained the sample size of 20, and so n sub 2 equal 20. The mean reduction in pain is y sub 2 bar equals 0.44, and the standard deviation is 1.4. We seek to answer the question, does it appear that magnets are effective in treating back pain? The mean given is the reduction in pain, and so if the magnet treatment is effective, if it is better than the sham treatment, then it should have the greater in reduction in pain. If we let mu1 be the measure in pain reduction in the magnet treatment subpopulation and mu2 be that in the sham treatment, then what we are interested in is to check whether mu1 is greater than mu2. We want to check if the reduction in pain in the first subpopulation with the magnet treatment is better than the reduction in pain in the sham treatment subpopulation. For our purpose for hypothesis testing, therefore, we can say that the initial claim is mu1 is greater than mu2. The opposite of this is mu1 less than or equal to mu2. Similar to the process of hypothesis testing for the null and the hypothesis, with the two statements, the one that does not have the equal sign will be the alternative hypothesis. Thus, the null hypothesis is the statement of indifference mu1 equals mu2, and the alternative hypothesis is mu1 greater than mu2. In some cases, we want to rewrite this as the null hypothesis is mu1 minus mu2 equals 0. So we can see that the null value is 0. And if we write it in this form, then the alternative hypothesis is mu1 minus mu2 is greater than 0, where we simply rearrange these inequalities. Now that we have the null and the alternative hypothesis, the next step is to compute the test statistics. In this case, sigma is not given, so sigma is unknown, so we will use the t-test statistics. The t-test statistic is t equals y1 bar minus y2 bar, the difference in the sample statistics, minus mu naught 1 minus mu naught 0, but the mu naught is the null value. So this is minus 0 divided by square root of s1 squared over n1 plus s2 squared over n2. And we have all of these quantities. Y1 bar is the average pain reduction in the magnet treatment sample, and it is 0.49. Y2 bar is the average reduction in pain in the sham treatment. It is 0.44. Minus the null value is 0 over the square root of S sub 1 is the standard deviation from the first sample. It is 0.96, and we squared it because in the formula it is squared, divided by n sub 1, which is the sample size from the first sample, plus S sub 2 is the standard deviation from the second sample, 1.4, and we square this, divided by n sub 2, which is the sample size from the second sample. Put everything in a calculator, we should get 0.132 for the test statistic, the t-test statistics. With the t-test statistic, when we find the p-value, we would need to know the degree of freedom. For the two variable, the degree of freedom is the smaller of the two, n sub 1 minus 1, n sub 2 minus 1. But n sub 1 minus 1 is 20 minus 1, which is 19. The sample size for the second sample is also 20. The smaller of the two, it has to be 19. We pick one that is smaller, but in this case, they are both the same. And so the degree of freedom is 19. With the test statistic t equals 0.132, with the degree of freedom equals 19, we find the p-value using either the t-table or a calculator. This is the one-side test because the inequality in the alternative hypothesis is the right tail greater than. And so the p-value is simply the probability that t is greater than 0.132 with the degree of freedom equals 19, and we see that this is 0.4482. Since the p-value is greater than alpha, alpha is the significant level, and we are asked to use alpha equals 0.05, we would fail to reject the null hypothesis. Remember that the null hypothesis is mu1 minus mu2 equals 0, or mu1 equals mu2, and we fail to reject it, meaning we support this. And if we support the null hypothesis, then we would need to reject the alternative hypothesis, which is mu1 greater than mu2. But this is the initial claim. The initial claim is that the pain reduction in the magnet treatment is better than the pain reduction in the sham treatment, and we reject this. We then conclude that the magnet treatment is not an effective pain reduction treatment. It is not effective. We failed to reject the null hypothesis because the p-value is high, and the reason why the p-value is high is because the test statistic is close to 0. And so if the test statistic is larger, then it is possible that the p-value is smaller, meaning we can make this p-value smaller by having a larger test statistic t. Remember that this is from the sampling distribution, and the p-value is this probability here on the right hand side of the test statistic for the right tail test, and in the middle it is the center, so t equals 0. This means if we want a smaller area on the right, the smaller p-value, then we would need to have t further apart, a larger t. And to get a larger t, it is possible to do so by increase the sample size. And so in this case, it is possible that if we increase the sample size, then we would make the p-value smaller. In turn, we would reject the null hypothesis. And so it is possible that the magnet might appear to be effective if the sample size is larger. We will compute the test statistic and the p-value again, but this time using a statistical software. A lot of the paid version of the statistical software or calculator can do this easily, but we will use the free Desmos. Just simply Google Desmo 2 sample t-test, and this is the one of the difficult tasks here because we need to know which calculator to use. In this case, if we do not know that we need to use the 2 sample t-test, then we will not be able to look up for this calculator. The first results in the search engine is the 2 sample t-test, and this is what we will see. We have sample size for the sample 1. It was given in the problem 20. The mean or the average for the first sample, it was given in the problem as well, 0.49. Standard deviation for the first sample, it was 0.96. Sample size for the second sample, 20. The mean for the second sample, 0.44. And the standard deviation for the second sample, 1.4. After we're done inputting all of the necessary information, or in this case, the statistic from the sample 1 and sample 2, we open the t-test calculator tab, and we see that the t-score is 0.132, and that is what we had earlier. For simplicity, we used the degree of freedom to be the lesser of n sub 1 minus 1 and n sub 2 minus 1, but with the calculator, they compute a better degree of freedom. In fact, the degree of freedom should be 33.6, and again, this is way too complicated. That is why we did not use this. This is the right tail test, and so we would have to open the correct tab here, and it is the right tail that we want. And notice that the p-value is 0.448, and also that is close to what we got earlier,